Did you know that the Earth just had a near miss with a cosmic slingshot? And I'm not talking about a Hollywood movie. Just a few weeks ago, a comet named 3I Atlas did something astronomers rarely get to see up close. It buzzed past our planet, and its path was altered, shifted by Earth's gravity. Imagine a celestial game of pinball where our planet is the bumper and this icy visitor is the ball. This isn't just a cool space fact, it's a groundbreaking moment for science, and thanks to incredibly precise timing, we caught the whole thing in action. How did we do it? And what does this tell us about the cosmic dance happening all around us? Stick around, because we're re-diving deep into the story of how we witnessed a comet's path being rewritten in real time. Let's start with the star of our show, Comet 3I Atlas. Now, this isn't your average run-of-the-mill comet. The I in its name stands for interstellar, meaning it's not from around here. It's a visitor from another star system, a traveler that has journeyed through the vast emptiness of interstellar space for millions, maybe even billions of years before wandering into our cosmic neighborhood. Think about that for a second. This object has seen things, orbited stars we can only dream of, and now it's right here in our backyard. It was first spotted by the Atlas Survey in Hawaii, which stands for Asteroid Terrestrial Impact Last Alert System. Their job is to scan the sky for things that might get a little too close for comfort, and they certainly found a fascinating one in 3I Atlas. Unlike comets born in our own solar system, which follow predictable elliptical paths around the sun, interstellar objects are wildcards. They come in on what we call a hyperbolic trajectory, a one-way ticket through our solar system. They fly in, swing around the sun, and fly right back out into the void, never to return. This makes every observation incredibly precious. We get one shot to study these emissaries from other stars. Before 3I Atlas, we'd only confirmed two other interstellar visitors, Oumuamua and Borisov. Each one was unique and taught us something new. Oumuamua was weirdly shaped and rocky, while Borisov looked more like a traditional comet. So, what secrets was 3I Atlas holding? As astronomers tracked its journey, they noticed something exciting. Its path was going to take it relatively close to Earth, close in astronomical terms. Of course, still millions of miles away. But this presented a golden opportunity. We know that massive objects like planets have a powerful gravitational pull. When a smaller object, like a comet, flies by, that gravity can act like a slingshot, either speeding it up and flinging it away, or slowing it down and altering its course. This is called a gravitational assist, or a gravity slingshot. NASA uses this trick all the time to send probes like Voyager and Juno to the outer planets, saving huge amounts of fuel. It's a fundamental principle of celestial mechanics. The big question for 3I Atlas was, could we actually measure this effect on an interstellar object? The change would be tiny, almost imperceptible. The comet is moving at an incredible speed, tens of thousands of miles per hour. The tug from Earth's gravity over a relatively short period would only slightly nudge its trajectory. Predicting this is one thing, but actually observing it and confirming the change is a whole different ballgame. It requires ridiculously precise measurements. We're talking about timing its position in the sky down to the millisecond and measuring its location with pinpoint accuracy. This is where modern astronomy really shines. A team of scientists using a global network of telescopes decided to take on this challenge. They knew the before trajectory of the comet with extreme precision from months of observation. Their goal was to measure the after trajectory, right after the comet made its closest approach to Earth, and see if it matched the predictions. Think of it like trying to measure how much a speeding bullet's path changes after flying past a powerful magnet. You need ultra-high-speed cameras and perfect timing. For the astronomers, their cameras were sophisticated telescopes, and their stopwatch was a network of atomic clocks. They pointed their instruments at the comet and waited. As 3I Atlas swung by our planet, it passed through Earth's gravitational sphere of influence. The invisible hand of our planet's gravity reached out and gave the icy traveler a gentle but firm tug. On the other side of this encounter, the telescopes locked back onto the comet. The moment of truth had arrived. The astronomers began crunching the numbers, comparing the new positions with the old ones, and accounting for the predicted gravitational pull. And then they found it, a tiny but unmistakable deviation. The comet's path had shifted. It was a few minutes off from where it would have been if Earth hadn't been there. Just a few minutes in time, which translates to thousands of miles in space. They had done it. They had successfully measured the gravitational shift of an interstellar object caused by our own planet. This is a massive achievement. Why? Because it confirms our understanding of gravity works perfectly, even on visitors from other star systems. It's a beautiful, real-world demonstration of the laws of physics that Newton and Einstein laid out centuries and decades ago. But it's more than just a textbook confirmation. This precise measurement allowed scientists to refine their calculations of the comet's trajectory. That tiny shift, that few minutes difference, contains a wealth of information. By analyzing exactly how much the path bent, scientists can better understand the comet's mass and density. It helps them build a more complete profile of this interstellar wanderer. What did we learn? This observation helps us understand the diversity of objects floating between the stars. By seeing how 3I Atlas reacted to Earth's gravity, we can compare it to our own solar system's comets. Is it more or less dense? Does it behave as expected? Every piece of data helps us build a bigger picture of what other solar systems might be like. Are their comets similar to ours, or are they fundamentally different? These are the questions that drive planetary science, and 3I Atlas just handed us a crucial clue. Furthermore, this success is a testament to our incredible technological capabilities. The ability to coordinate multiple telescopes across the globe, to time observations with sub-second precision, and to process that data to find such a subtle signal is simply astounding. It shows how far we've come in our ability to probe the cosmos. It's like being able to hear a single pin drop in the middle of a roaring stadium. This level of precision opens up new possibilities for future observations. The next time an interstellar object flies by, we'll be even better prepared to study it in exquisite detail. So, the next time you look up at the night sky, remember this incredible story. We live on a planet that is an active participant in the cosmos, a gravitational heavyweight that can literally redirect the paths of travelers from other stars. And on this planet, we have people with the curiosity and the ingenuity to watch it happen and understand what it means. We caught a comet shifting its course in real time, a beautiful, fleeting moment in our solar system's long history. It's a powerful reminder that there are always new wonders to discover right in our own cosmic backyard. Thank you so much for joining me on this cosmic journey today. If you found this as fascinating as I did, please hit that like button and consider subscribing for more stories from the frontiers of science. Let me know in the comments what you think about these interstellar visitors. Until next time, keep looking up.